So last year, we sat at the end of the conference and took stock. Should we do it again? And I think the answer is obviously yes. But I remember wondering, if we come back in a year's time, like last year, we'd taken so much of this cool stuff from across the local first spectrum and we brought it to the conference. Will things have actually moved on in a year? Or are we just going to be regurgitating the same stuff, the same ideas? And I think we can see, right, from the talks already today, how things have come along, right? The tooling has really matured. The thinking has moved forward. There's a lot more clarity. And so, things have developed as well with us at Electric. And our thing at Electric has always been about mainstreaming. It's trying to be an on-ramp for mainstream adoption of local first. And so, whilst my talk is called Introducing TanStack DB, and I will, it's really about the concept of sync. And it's about how this concept is crucial to mainstreaming local first. So this time last year with Electric, we were building a local first software stack. We were targeting brownfield adoption, so it works with your existing data model, your existing stack, and we were trying to make it batteries included. So we had things like a type-safe client built off your database schema. We had automated migrations. We had a conflict-free write path. We were trying to hold on to guarantees like no conflicts, like finality of local rights. And it was a bit too much, right? We were struggling with the complexity of delivering on that proposition. Things like permissions, the data model support, working with all of the weird features that people have in real-world data models, constraints, referential integrity, right? And it felt, as a development team, a bit like playing whack-a-mole. You'd fix one bug, bang, and like 3 more come up, bang, 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 and then more come up. And so the surface area was just too large. And so when Kyle joined, we stopped everything that we were doing, and we took a step back, and we went right back all the way to the beginning, when we literally started again. So we did a clean rewrite of our core product, the Electric Sync Engine. And the thinking was to kind of slim it down, reduce that surface area, and then push stuff out of scope where necessary or where we could, and focus on making something small that really worked. And that thing for us was a read path sync engine. So take data out of Postgres, filter it, and then fan it out into local apps and services. And we wanted to make this sync engine reliable and performant while still taking on the challenge of partial replication. Like how you get the right subset of data synced to the right client. But in our case, we wanted to keep the partial replication primitive, which we call a shape, deliberately simple. So it is just a filtered view of a database table, because that way we could do this and avoid exploding resource use. So if you're trying to do things like joins or include trees, then you have to maintain state, and there's extra compute, and it can just explode in terms of sort of memory use, compute use, storage. And we chose to change our sync protocol from a binary protobuf system over WebSocket to just old-fashioned HTTP and JSON. And it may sound like a regression, but we chose to do it because it allows us to deliver data through existing CDN infrastructure. And so that was the plan, and we built it. We started in June. We shipped the first alpha release in July. We iterated a lot, and thanks very much to all of the feedback and experimentation from users in the community that helped us develop against. And we hit beta in December. And we kept going, and we were fixing bugs, and we were improving performance, and that led to more and more production use, which led to a 1.0 release this March, quickly followed by a managed cloud release in April, so you can just give us a Postgres connection string, and we run all the sync infrastructure for you. And through this, we've done all we can to hold on to that key objective, which was like, keep it simple enough so that we can actually make it just work. And not just work, but also scale out of the box. So here we're showing scaling up to 1 million concurrent clients collectively syncing an 80 gigabit per second workload, and that's coming out of one small electric server on top of a single commodity Postgres. And it's doing it with flat latency, so as it scales up, the latency doesn't increase, and it is flat memory, flat resource use on the server. And as well, because it's just HTTP and JSON, it allows you to do sync through and with your API, which can be any web framework, any language, any middleware, any proxy, any client, any data model. It's not our stack. It's your stack. And that is really important, both to the development model, but also to this incremental adoption pathway. And so where we imagined we would go next would be like more expressive shapes, rich shapes we call them, adding support for things like joins, include trees, etc. And then also maybe adding back support for right path sync and these other aspects of the stack that we had pushed out of scope. But actually, what we discovered was that our users were already finding ways to be successful within the constraints of this simplified system that we'd rebuilt. And so, for example, whilst the core shapes out of Electric are just filtered tables, users were actually implementing more expressive shapes themselves in their back-end API or in edge workers as proxies in front of the system. So they were proxying the stream and then like joining and transforming the output. Or they were syncing shapes into the client, and then they were joining up the data and building incremental views, etc., just in their JavaScript code. So, for example, writing stuff like this. So you're syncing in data, maybe some kind of high-level filtering, like a workspace ID or kind of authorization. And then they were looping over it in the client to build the views that they needed to bind to the components, right? And this is just example code to get the idea across, but it's the kind of thing that people were writing. And even though it's hacky and it doesn't scale, in many cases, it was getting the job done. And with write, we had documented a bunch of patterns to work around our lack of write path support, which are all basically based around posting data to your API, but with various techniques for managing optimistic state in the client. And actually, these patterns went down really well. So for example, one of the simplest was to use React's built-in optimistic hook. Just gives you a function that applies local optimistic state until a transition resolves. And then you use it in your app like this. So you make a local write, it applies optimistic state, you can send the write to the server, usually with some sort of resilient retry logic, and then you wait for it to sync back through and discard the optimistic state. And so what we found is that teams were shipping real products with real users on top of these patterns. And so it was clear to us that instead of carrying on with what we'd imagined we would be developing, these were the desire paths that we should pave over. But of course, at Electric, we are focused on brownfield, incremental adoption by mainstream developers. So we didn't just want to lay the concrete in isolation, we want to connect those paths with the road network. And not just the road network, we want to connect them with the motorway, the Autobahn. And so, where is that motorway? Where is the mainstream of application development? Well, really, you dig into it, and there are two games in town, right? There is Next.js doing server-side rendering. It's a bit complex. It's not the best fit with local first. And then you have more purist single-page apps. And so if we focus there on this single-page application development, what are people using? So what is the mainstream? It's TanStack. So what if we could build support for these patterns that we've been seeing directly into TanStack. What would that be? Well, TanStack grew out of React Query. It's now called TanStack Query. It gives you like managed queries, caching, mutation primitives, etc. It already has primitives like a signals-based reactive store. And if you look at what it looks like to actually use it, right, so this is idiomatic TanStack query code. It loads data into a React state variable using a managed query function. So the function defines how you fetch the data, and then TanStack query manages calling it, retrying it, etc. And then when it comes to write, what you do is you create a mutator using this use mutation hook, and that has a mutation function that defines how you then actually handle the write. In this case, posting it to your API, and you then use this mutator in your components to make local optimistic writes. And so this is how a lot of apps are currently built, right? This is the code that developers are used to writing, and it's the code that LLMs are extremely used to writing. And so like Ansem says, you want to get the LLMs writing local first, well, you want local first to look just like this. And so what do we actually need to do, given those existing primitives and that developer experience, to add local first into TanStack? Well, you need to change from fetching the data using the managed query primitives to syncing the data so you have the data locally. And that means we need a primitive to sync into, and then we need the local mutations to apply optimistic state to this primitive, and we need to handle the writes by syncing them in the background and tie in the optimistic state lifecycle in with the sync machinery. And we need to pave this desire path of joining data up and building views on the sync data in the client, which means you need live queries to be able to query across these collections, this primitive. So let's recap on what we need to add to TanStack. We need a collection primitive. You need sync to keep the contents up to date. You need live queries across collections. And you need a way of handling the local optimistic writes that not only works with the write path sync, but also monitors the read path sync in order to automatically manage the optimistic state. And so if you have this, you have a fully working local first stack built natively into TanStack. And so Kyle and Sam on our team saw this, and Tanner from TanStack was also seeing exactly the same ideas. And so they agreed to collaborate and build it. And so today, I am very pleased to introduce and announce the result, which is their work, which is TanStack DB. So it's a library we built into TanStack that extends TanStack query with collections, live queries, and transactional mutators that with robust management of optimistic state that works natively with both read path and write path sync. And the key idea here is that it allows developers to incrementally migrate just existing cloud-first applications that are built on standard REST APIs querying, for example, built with React Query, to query-based applications using TanStack DB, so where the queries are loading data in locally and you switch the application code to then talking to a local store, to then be able to incrementally move to sync-based applications using TanStack DB, where the local store is wired up to a sync engine, and then to a fully local-first architecture that's reactive, consistent, offline capable, and as we will see, insanely fast. So let's dive in and see how it works. So you start by defining a collection. In this case, we're defining a query collection, and this loads the data using a managed query function. And so we've seen this code before, right? So the change to your application to use this for a React Query developer is just minimal. And then when you have data in collections, you can bind it to your components using live queries. And to write data locally, rather than the use mutation hook we saw before, you use optimistic mutation instead, with a mutation function that handles sending the write to the back end. And so in this case, it posts it to your API, and then calls refetch on the collection to invalidate the data and trigger a refetch. And then to use this mutator in your components, you just call mutate. And this starts a transaction, and all the writes made within it are instantly applied locally, and the background sync, and the optimistic state lifecycle, and any necessary transactional rollbacks, it's all handled for you. And so that is the migration pathway from React Query to TanStack DB. But of course, TanStack DB is not only designed to work with queries, it's also designed to work with sync. And so the way you do that is instead of defining a query collection, you define an electric collection like this. And this keeps the contents of the collection in sync with the shape defined in the stream options. And if you've used it, these are just the options you pass to the electric client when you're syncing a shape. And you can define whatever filters you want. So remember, a shape is just a filtered view on a database table. And you can create as many views of those as you want with different subsets of the source data coming into the application. And it's worth emphasizing, this is an electric-backed collection, and that's already built into the TanStack DB library, but anybody can implement their own collection types. So anybody here with a sync engine can basically just implement this interface, and you'll have TanStack running on top of your sync engine. And then to query the data, the component is just exactly the same as before. The components don't need to know where the data came from, right? They just work against the local collections. Except, we've actually now defined two collections, right? We've got the previous to-dos collection, which was a query collection, and we just defined a new users collection with electric sync. And so what we can do is demonstrate querying across collections. And you can query across as many collections as you like, and they can be collections of different types. So you can load some data from the database. You can load some data from an API. We have a local collection type for UE state. And you can then basically query across all of those things as part of the same logical data model in the client-side application. And you can have as many complex queries as you like with multiple tables and joins and aggregates, etc., because the query engine is based on a TypeScript implementation of differential data flow. When the data changes, it incrementally updates just the relevant part of the result set. And so obviously Aaron talked a bunch about this already, and we mitigate that key hydration challenge with D2 slightly by already pre-filtering the data when it comes into the client using shapes. And also we allow you to predefine layers of your query. So they're updated when the data syncs in, and then when you define dynamic queries at runtime from your components, you can reduce the set of the data, the amount of the data that you need to run through the hydration step. So we're never pumping in that whole data set. And so in practice, if you look at the actual performance, this is a little benchmark that Sam just knocked up yesterday. I'll skip the details. There's basically three very complicated queries. They're all running multiple joins across multiple tables with lots of rows in there using grouping and aggregates, etc. The basic JS is basically like hacking it in JS, like that first hacky script I showed you. SQLite is rerunning the queries against the database. And TanStack DB, basically across all of them, is sub-millisecond, no matter what. So the key thing is just instead, when you build against this model, if you start off with like a component and a live query and it works great, and then you add more and more components into your application, they're all doing their own live queries, it starts to grind to a halt if you're having to kind of re-query the data all the time. But in this case, you can have loads of components all making lots of complex live queries, and it all stays within that single animation frame that Adam was talking about. And so we've seen the component code stays just the same, but the queries are actually really powerful under the hood. Well, the same is true of mutations. So you've switched your application to sync, but the component code is completely untouched. And if you want, the mutation function to handle writes can just be exactly the same as it was before. You can just handle writes by posting them to individual endpoints. But if you choose to, you can move incrementally to write path sync with a generic mutation function. So this is all of the code you need for this. And what we're doing here is whenever there is a local transaction applying changes to any collection, you give it all the same mutation function. And you just post the mutations to the back end, to a generic ingest endpoint. If the transaction's rejected, it's rolled back locally. And if it's successful, the key requirement is that the server returns the transaction ID that the changes were written into the database under. And then the machinery monitors the replication stream for that transaction coming through, and then discards optimistic state when it arrives. And this is actually both simple and pragmatic, but also very powerful. So it's simple in the sense that it's server authoritative, you just have rollbacks, but it's sophisticated in the sense that because you're matching on the transaction ID, it allows concurrent updates from other users to come in and have the local optimistic state rebased on top of them until your transaction actually comes through the replication stream. And then on the server side, you just ingest the changes. And obviously, you can just do that in any language, any framework you like, right? This works with your API. It's your stack. And so one reference implementation that we've done of this is Phoenix Sync. So Phoenix is the web framework for the Elixir programming language. It's kind of the new Rails, right? It's popular with startups. It's like most loved web framework, 2 years running. And Phoenix Sync is an official sync library that we collaborated on with Jose Valim and Chris McCord, the Phoenix framework authors, and it works with TanStack DB out of the box. And so actually as a sync library for Phoenix, it does a whole bunch of stuff, including allowing you to sync shapes through your backend router. You can use your controllers as proxies. You can construct dynamic shapes. And because it's all over HTTP, you can use your existing auth middleware and logic to authorize both read and write path sync. And something really important with this model is that if you're coming from an API-based application, you don't have to codify your authorization logic into a database rule system. You can just use your existing back-end auth logic or middleware. And then with this system, with writes, you just ingest them using a normal controller and just write them to the database. And like this Phoenix Sync library provides some utilities, like returning the transaction ID to match on I mentioned, but also more powerfully, it provides a declarative pipeline for ingesting mutations. And again, this allows you to reuse your existing backend logic that you may have to authorize and validate writes that you've written for your API-based application, and just reuse them on an ingest pipeline for write path sync. So if you're not an Elixir Phoenix developer, this may look a bit odd and weird, pipe syntax, but the same pattern applies in any web framework, any language. And so this is what we've been trying to do at Electric, is build primitives that we can integrate into mainstream development frameworks with this incremental adoption pathway so that developers can move towards sync and into local first, one fetch, one route, one ingest at a time. And importantly, so that you can do that with your stack of choice. And we call the concept for that the sync stack. It's like Sync's answer to Jamstack. It's not a particular technology, it's an architecture, it's an approach to building applications. And it's a concept we're going to be promoting. But again, it's not an Electric thing. Yeah, your sync stack could be Phoenix Sync and TanStack DB, or it could be Electric and LiveStore, or it could be Zero, or it could be Jazz, or it could be Instant, or it could be PowerSync with TinyBase or Legend State, right? The sync stack is an idea that actually all of us here in this room can promote. And that's why, as well as, when reflecting on it, deciding to run Local First Conf again this year in Berlin, we also decided to run SyncConf in San Francisco this November. And it's a conference for anybody interested. So it's a conference for anyone interested in building on sync, which in San Francisco means a lot of startup founders, people building AI apps, agentic systems, which we know from Anselm's talk and other discussions is just one of the areas where sync really shines. Like AI apps are just naturally collaborative. You have multiple users, multiple agents. They have to be built on sync. And we're also running sync meetups. We have one in London on the 1st of July. We also happen to have one in Ghent, actually this Thursday. And it's because this concept of sync is what's going to provide this on-ramp for mainstream adoption of local first, right? And that's how we see these things fitting together, this first question in the panel discussion. And TanStack DB is the gateway drug. Thank you.